afternoon. I will spend most of the time talking about SuperLU, this library we have developed for quite some years. But I'd like to spend the last few minutes to talk about this new library, STRUMPACK. It is also based on factorization with a little bit approximation. So it can be used as a direct solver, but probably in most scenarios, it should be used as a preconditioner. I'd like to thank all the, over the years, all the funding agencies have supported the development of this work. Without this support, obviously, the library cannot be developed, the software cannot be written in a good way. And also, over the years, we have a lot of contributors from different places, different countries. And then at this link, you can see all the user documentation, user guide, HTML code documentation. Once you download each tar file, you do on zip and on tar, you get a bunch of directories. At the top level, there's a README file. You really should read that README file carefully. Since right now the build process is not very automatic. Essentially, you need two steps. One is to edit. There's a make.inc for each platform, for your platform, which defines compilers, optimization flags, the libraries where you want to link. Then the performance-wise, the big thing we rely on is the BLAS library. For many people on their machine, they probably don't have a fast BLAS library. And in the SuperLU distribution, we have this CBLAS subdirectory, which you can compile a working version of the BLAS. It's by no means fast, high performance, but it's working. So in the very beginning, if you don't have BLAS, you just want to test the code, whether it works, just to use this CBLAS library. Alternatively, the better solution is to use a vendor BLAS, many high-performance machines. And there's a GoToBLAS and also Atlas. So we are in the process of creating the CMake build system to automate this process. The tutorial outline is out. Tell you the functionality of the libraries, and then the sparse data matrix format, how it's distributed, what's the user interface look like, and a little bit of background of the algorithms, which is helpful for you when you encounter any problem, especially performance-wise. And I'll show you some examples, and in particular, the Fortran 90 interface. And then later today, there's a hands-on exercise session. It's difficult to say what do you mean by how sparse the matrix would be if you consider that as sparse. Essentially, is if the matrix is sparse enough, using a sparse code can benefit in terms of memory and runtime compared to using a dense LU code, then you should use this sparse code. There are a lot of applications. And a typical example from the PDE world is that your matrix could have an arbitrary dimension. But then for each row, on average, for each row, it's usually just number of non-zeros is tens or hundreds. It doesn't grow with the matrix dimension. And then depending on the applications, you could have different non-zero sparsity patterns. For example, I gave you these two different applications. One is from the structural engineering. The other one is from chemical engineering. And then you can see their non-zero patterns are very different. This structural engineering one looks more regular. It looks very nice. But the chemical engineering one looks more harder to handle. But our solver is algebraic solver. We can handle any sparsity pattern. So that's not a problem. I can show you the data structure. There are two big categories of solution methods. One is the iterative methods, including Krylov methods and multigrid. In this category, it's very nice. The matrix A is not changed. So A is only read-only. The sparse matrix is only read-only. Then there are a lot of operations which involves sparse matrix vector multiplication. For these kind of kernel, sparse matrix vector multiplication is much easier to optimize on modern machines and also to parallelize. It has low arithmetic complexity. But the drawback, of course, may not converge. And the second bigger category is direct methods. That's what this LU is for. The biggest problem with LU is A is modified. You have to factorize this matrix, and it's not just the read-only. And also, it's harder to optimize parallelize. Numerically, it's more robust, but with higher arithmetic complexity. And very often in nowadays, the large-scale calculations, we often use the direct methods to precondition iterative methods. So the outer loop is iterative, maybe Krylov loop, but inside you use a direct method. So the operator you are looking at to solve the linear system is a transformed system, M inverse AX, like this. And your M inverse is probably some part of the factorization, of approximate factorization, for example. And there are quite a number of sparse direct solver codes developed over the years. Their support and the usability it varies. So I try to keep a small survey article with a table of different codes. Then you can do different kind of factorization. For example, for SPD, you do LL transpose. For symmetric indefinite, it's LDL transpose and LU, QR. And some of the codes are developed just sequential, some shared memory, some distributed memory. More recently, there are codes some codes available. They can do take advantage of GPU. For example, SuperLU dist. Right now, we have a GPU capability. So those I still need to update this table, but you can take a look afterwards. For distributed memory code, it's relatively harder to write. There are not so many. So our group has been working on SuperLU dist. And this is accessible from PETC. Trilinos Hyper, I think, also uses this. And there's also a popular one, MUMPS and PASTIC, WSMP from IBM. So in SuperLU, we do LU factorization triangular solution. Those are the basic functionality to solve a linear system. In the sequential code, we also have this incomplete LU as a preconditioner. It's based on supernodes also. And then you can do a lot of other things. You can solve transpose the system, multiple right-hand side. When you do one factorization, solve many systems. And then we have a sparsity preserving ordering with the option of a minimum degree Nancy dissection. And for numerical pivoting, user could give a threshold. So you can trade off the sparsity with the numerical stability, depending on what threshold you gave. And then there's some other functionalities which is very useful for increase the robustness of the solver, so like equilibration to help reduce the condition number of the linear system, and the condition number estimation, which helps you to understand how poorly conditioned your system is and what kind of accuracy you can expect from this, say, very poorly conditioned system. And then we do give component-wise error bounds, so that could tell you how many digits you get correct after the solution. The library has three different branches. One is purely sequential. The other is purely multi-core shared memory. And the last one is a distributed memory. So now the distributed memory, we have C plus MPI plus OpenMP to take advantage of each node has many cores. And also with CUDA to enable access to NVIDIA GPU. And in the future, this CUDA could be replaced by OpenCL or some other standard language library to access the other GPU cards. So this is a little cartoon of a sparse matrix of dimension 7 by 7. I only have non-zeros marked here. And the dimension is n is 7, and z is 19, number of non-zeros. Then I need, for this compressed row storage, I need 3 arrays. One is NNZ reals, which has to store all the non-zero values. And then the other 2 arrays, they are integer. The total size is NNZ plus n plus 1 integers. So if you look at NNZ real in this compressed row storage, so you do first row, second row, third row, etc. Line them up in a one-dimensional array consecutively. And then you have the boundary here, each row boundary here. And then for each of these non-zero, you have the column index. So for example, for this C, column index is 1. For this G, column index is 7. Okay? And also they have the same boundary, the row boundary as the values. And to determine the boundary of each row, there's a third array, which is the row pointer, which points to the beginning of each non-zero rows. So the first one starting from 1, the second row starting from position 3, the sixth row starting from position 13 of this. So between the 2 pointers here, between 11 and 13, you know that there are 2 non-zeros in the 5th row. Okay. And then this is compressed row-wise storage. You can symmetrically have a compressed column-wise storage in the same way. And there are many other compressed compact data structures. You can read this book, Templates for the Solution of Linear System. It has a summary. And then the interesting thing is how do you do this in a distributed fashion? So in the distributed interface, users need to input A, B, and B will turn into X, the solution. So users need to input the AB matrix. And internally, we have LU factors. You don't need to know the data structure of LU. Okay, so let's take a look at AB, what you need to know. So suppose I have 3 processors here. Then I partition A in 3 block rows. They can have different number of non-zeros. And you tell me the boundary of each processor, what I'm getting. And you have to make sure the B could be 1 column or multiple columns. They have the conforming partition as A here. So look at this partition. And this is called compressed row format, but it's distributed. And a data structure that describes this for each processor on each local processor is you only need to feed in these 6 items. One is number of non-zero local, how many non-zeros on my processor, and M is number of rows local to my processor. And then the first row starting, it's the global index. Tell me where your current block row is in the global matrix starts. And then you have the NZ-val, these 3 arrays as a standard CRS format. So once every processor has their local data structure, then the library could communicate to figure out the global matrix image. And once you set this up, you don't need to worry about the global image. So this is a small example here. A small 5x5 matrix have 2 processors. So let's see what P1 on this processor you need to put in the data structure. You want to say that NNZ local have 7 non-zeros. M local has 3 rows, okay? And the first row here, we start from 2. So this is a C-based indexing starting from 0. The code is implemented in C. So the first row is starting from 2 in the global matrix sense. So you need to tell me this. And then the NZ-val is 1P-EU-LLR, like this. And column index, corresponding column index, the row pointer, it's starting from 0 to 7 for each of these 3 rows. The last one is just a 1 end pointer. Okay. So the internal structure, even though you don't need to know, but one thing you need to set is the process grid. So that's why I'm still explaining this. Internally, in order to get a more scalable factorization, we use this 2D block cyclic layout, which is very similar to dense scalar pack the use. But of course, the difficulty here is the non-zero block size. They don't have the same size. You could have different sizes of the non-zero block. And essentially, we use something called supernode to get the partition of the non-zero block, both row-wise and column-wise, and then map these non-zeros, zero blocks to this processor mesh. And the question for the user you need to do is to input into the library is to set this process mesh. The biggest problem, sometimes the performance hit, is if you don't set this in properly, the code might be quite a bit slower. The general rule is you want to give this as a square as possible. But if it's not possible to be, it's not a square number of processors, then you give row dimension slightly smaller than the column dimension, just because this algorithm has more communication along the row dimension. So you don't want the row dimension to be very big. So the worst case scenario, for example, for 32 processors, the worst case setup is 32 by 1. So you want to do 4 by 8. Okay, even 8 by 4 is slightly worse. Okay? So that's all you need to know. And then the processor grid for MPI communicator. This is useful because very often in big applications, this SuperLU is used as a preconditioner. One popular preconditioning scenario is a block diagonal preconditioner. So you have a matrix here, the global matrix, but you only take the diagonal block of certain size you choose. You want a diagonal block to be inverted or factorized, and then to use this pink stuff to inverted pink stuff to precondition the global matrix. So in this case, you may want to run parallel SuperLU on each of these A11, A22 block. Okay, so that means you want to, for example, if you use 12 processors, you divide into 3 groups, and each group we will use 4 of those processors. So this usage scenario is supported. What you need to do is you call this a SuperLU grid map, which will map the physical processors to the processor I'm going to use in the library in this communicator. So for example, if you want to run using 6 processors to solve a problem, to solve one linear system, but these 6 processors may be physically numbered from 11 to 16. So you just need to give this physical number to the library, tell the library you have this user map, which is given by this. And then the library will know that I'm going to use this 16 instead of this is 6 instead of the other processors to solve this linear system. So I'll talk a little bit very quickly about the algorithm. It's useful to understand how you use the library. So the sparse factorization involves a lot more compared with dense LU. And one of the biggest problem is the filling. So this little cartoon here on the left is the small matrix. The black dots are the non-zeros to begin with, your matrix A. But when I factorize that, you will get in addition to the black dots, also the red dots. So these red dots are called the filling. So it's originally zeros, but become non-zero. And it can actually have a lot. It's quite dramatic. So in practice, when we see the 2D problems, we see very often it's 10 times filling. So that means the LU size is 10 times more than A. Then you can imagine it's memory intensive. And for 3D problem, it's worse. 50 times is very common. Sometimes could be 100. Okay. And the thing is to find these filling elements, we need a very sophisticated graph algorithms to look at the sparsity pattern, formulate this as a graph, something like this and this. And then once you apply the graph algorithms, you can apply the partitioning on distributed memory machines, and also to do the scheduling of calculation. Also, there's something called the symbolic factorization to locate where the red dots will be. So you set up the data structure. So it's a lot more involved. And if you look at any sparse code, usually you can identify the 4 different phases. One is ordering. How do you order the equations to minimize the amount of fill? And the other is the symbolic factorization, which is to predict the filling position, set up a data structure. And then you design the data structure to allocate the storage to store those non-zeros. And finally, after all these pre-processing steps, you do the real factorization and solve. Time-wise, usually the numerical factorization solution dominates. That's why most of the parallel code you see, they focus more on this phase, not the previous phase. Also, the pre-processing steps, they are much harder to parallelize. But in SuperLU dist, we have parallelize of everything. including symbolic factorization, and we rely on the parameters, PT Scotch, for the parallel ordering. Okay, so then each of these phases, there's a lot of research in each, a large amount of research, and basically we try to absorb a lot of research ideas into the solver. So let's see. The reason this package is called a SuperLU, it's not because of its super something. It's because internally for LU, we are using this supernode data structure. So we identify the non-zero, consecutive non-zero columns. They have the same non-zero pattern. And then we can use a compressed representation for these 4 columns together. So throughout the matrix, we have a collection of supernodes. That's why it's called a SuperLU. And from the graph point of view, if you look at the adjacency graph of this part of the matrix, you have these 4 vertices. They are fully connected. So when we do the graph algorithm, we have a compressed, sparser graph of a smaller number of nodes to traverse. It's also more efficient. And also, depending on the sequential code or shared memory code, distributed memory code, we decide to use different pivoting strategy. The numerical pivoting is to make sure you don't get a large pivot element, so then you lose stability. So for example, at each step, you don't want this pivot element to be small. If you see a big one along this column, you have to swap these 2 rows. And this, of course, will cause the dynamic data structure change, sparsity change for the rest of the matrix for the future steps. That's not very pleasant for distributed memory code. So partial pivoting, when we do this swapping dynamically, it's only used in sequential code and the shared memory code, but it's more robust numerically. And then for the distributed code, we change the strategy. We use a static pivoting. We use a pre-processing step running the maximum weighted bipartite graph algorithm to put large elements of A on the diagonal first before doing the LU. And during the LU, if we still see small pivot, we'll bump it up to a larger element to avoid a division by small number. And in the end, if needed, you can invoke a couple of steps of iterative refinement. So that's the code setup. For the sparsity ordering, there are 2 different kinds. One is minimum degree, which means you start with a graph. Every time you choose a vertex with the smallest number of neighbors, you try to eliminate this guy first, do the Gauss elimination of this guy first. Once you eliminate this guy, the neighbors become a clique. You will generate non-zeros, the filling here. Some of them already exist, so they are there. But in the worst case, you can generate a lot of filling, the whole complete graph. So that's why each step you want to pick up the vertex with the minimum degree ordering. That's the idea here. This is the local greedy strategy. And the global strategy works much better for the large-scale problems from what we see. For example, for the model problem, this 5-point stencil, you have a 2-dimensional mesh like this. What you do is you partition the graph, partition the mesh at this line, for example. Then you decouple the graph into 2 pieces. And the nodes corresponding to this first level separator, they will be eliminated last. And then partition the graph for each of the sub-piece, then do this ordering, continue recursively doing this. It turns out with this nested dissection, it's a dissection, but at each subpart it's dissection. With this nested dissection ordering, you can prove optimality of factorization flops. So then this can be generalized to any sparse matrix algebraically. So you give a graph, you find a separator here, put the separator last, reorder, and then A and B second. Recursively do the nested dissection for A and B, okay? So 2 kind of ordering, and that's the ordering and the ordering result. Starting from this mesh, with natural ordering, you get this sparsity pattern. With nested dissection ordering, you get this pattern. And then after the filling, you see the nested dissection ordering that give you the filling number of non-zero. The red stuff, it stays within the separator. It doesn't go to outside this 0 block. Okay, so let's see. So for the user interface for the ordering, we actually could incorporate any other ordering method. So that means when you set up this option, you will say, I'm not going to use what you have provided. Because the ordering has a lot of newer research, you can just ask the calling any other library or your research code to get a permutation C vector to input into the library. Then I will use your permutation. This permutation is just a swapping of integer from 1 to n, right? And then symbolic factorization for symmetric Cholesky is easier. For LU is more involved. So I'll show you, you can read this later with different matrices from different applications. The filling ratio actually varies a lot. So for this matrix DNA application, the fill, amount of fill is over 600-fold. So it's tremendous. For circuit matrix, it's much better. It's almost stay no fill. And also for the, if you look at a strong scaling, this is on an older machine at NERSC. It's Cray XE6. Depending on the application, the matrices, some of them you get very good strong scaling up to several thousand processors. Some of them you taper at several hundred processors. So it's also it's not always uniform. And recently we added the multi-core GPU support. The result we have seen is with, for example, 100 nodes of GPU cluster, we get about almost 3 times faster compared to pure MPI. And the biggest saving is coming from memory. We get could get a 5-fold saving of memory. This is significant. So to use this interface, again, this is explained in the README. You use OpenMP, you have to set a number of threads, and then to use GPU, currently we only support NVIDIA. You have to set environment variable of this, so that because internally the library is spinning some code GPU related, and also insert some of these CUDA library paths into the make.inc. And there are some samples you can see in the distribution. And we also have a supernodal-based ILU, which we compared with the earlier version, the best algorithm before. We get much better results. So this can be used as a preconditioner. So for the performance debugging, one of the things is you first need to check sparsity ordering, whether you can use a good sparsity to make sure that you don't get too many fields. And you can try different versions. And then very often the diagonal pivoting is preferable, so you can use a diagonal. We have a symmetric mode to do. And BLAS is a big issue. That's most of the performance coming from BLAS library. And also block size, which can be set in this environment variable. So then we have for exercise on the machine Vesta, which the README file is in that directory, and all the examples are set up there. So this, I don't have time to talk about STRUMPACK, but it's based on the low rank approximation of some off-diagonal block of the matrix. And we use a hierarchical matrix concept, the algorithm, which makes the complexity of the algorithm much lower. And you can think about this as an algebraic generalization to the fast multiple method. So in this algebraic extension, you can do matrix multiplication, factorization, inversion, can solve linear system, which is something FMM cannot do. And that's the cartoon about how we do this in the dense and sparse case. And in the dense case, we compared with LU, we see the speed up is about 5 times speed up compared if you do this just as LU. Okay, and then we compared with Intel MKL Paradiso sparse library, use this STRUMPACK consistently for all these different matrices. They are from different applications. We get a better performance. Okay.